Next, we're going to try to show how to use the definition of discrete time Fourier transform to help us calculate spectrum for some common non-periodic sequence. The first one is impulse sequence delta of k. We can plug that signal into the definition of discrete time Fourier transform, and the result is DC components 1. So delta function in time domain corresponds to DC components in the frequency domain. The next sequence is unilateral exponential signal with the base equal to alpha. We can again plug that sequence into the definition of discrete time Fourier transform. In case alpha is greater than 1 or less than -1, the partial summation does not converge. And in case alpha is between -1 and +1, the value can be calculated as this equation. For example, when alpha equal to 0.7, here is the amplitude spectrum, and this is the phase spectrum. The next sequence is rectangle sequence with width equal to 2 times m plus 1. Here is the graphic representation of the rectangle signal in the time domain. We may use the definition again. So here is the definition. Plug that one into it, and here is the partial summation of the imaginary exponential signals. And we can calculate the partial summation and do a simplification. Here is the graphic representation of rectangle sequence with width equal to 2 times capital M plus 1. Using the inverse Fourier discrete time Fourier transform, we can also help us find out the original signal when the spectrum is given. So here is one example. If the spectrum is this function in the frequency domain, how can we figure out the original sequence in the time domain? We can use the inverse Fourier transform. So here is the definition, and we can plug this into that definition. That will be straightforward. We can get the final results. It's a sampling function. Thank you.